Hi, in this video we're going to be looking at different aspects of training and evaluating n-gram models. And we're going to split this into two parts. In this video we'll look at how we split our data so that we can train on some data and then test on another data, so that we can simulate how your model is going to go out in the real world and find new sentences all the time. We're also going to look at how we can measure the performance of the data. We're going to call this perplexity, or how surprised your model is at bumping into new sentences. In the next video, we're going to look at how we can deal with words we've never seen before. These are called out of vocabulary words. And we're going to look at how biases can creep into our model from the input that we use. So let's take this one step at a time. Let's start with training and testing. So let's say you want to build a model. This model is evidently going to have to go out into the real world and is going to be finding new sentences all the time. So you need to prepare it as best as you can for it to deal with these new sentences. The way that we can simulate that is by taking our data and separating a small chunk of our data that we will never use in the training. The training will never see it, but we will use it to assess how well we performed our training. So we're going to get this small test set and use it to assess the performance of the system. In this case, how well does our n-gram model predict sentences in this testing set, which is going to be our simulation of the real world. We also have a training test set, which is where the n-gram model is going to get its probabilities from. The bigram probabilities, the trigram probabilities, they're going to come from the training set. And these can be split in different ways. Sometimes they're 90% for training and 10% for testing. Sometimes they're 80% for training and 20% for testing, and so forth. So in this way, we split the data in two parts. A training set that we use to derive the probabilities of the n-grams, and a testing set. And we calculate the probability of each of the sentences in the testing set to see whether they are well predicted by our n-grams from the training set. We could also split this in three ways. And this is very common in machine learning. We have our original chunk for testing, let's say 10%. And from the other 90%, we take 10% of that out for something called validation. And with the remaining 90% of the sub-chunk, we do the training. So we perform the training and get our n-gram probabilities, but then maybe we want to do other things, like figure out if we want to use n-grams or bigrams or trigrams. Maybe we have some fancy smoothing algorithm that we're testing and we need to fine-tune. So we're going to use the validation set as a kind of internal test so that we can see how different options in the training phase are doing, and so that we can minimize the error during our training phase. Once we have trained and validated, we take this model, which we have improved upon, and test on the testing set, which are sentences that the system will never have seen before. This is very common for neural networks, for example, and other types of deep learning. So we can split in two parts, in three parts. What we can never do is mix the testing and the training. The technical name for this is peeking, for you to be peeking into your testing set. If you did this, you would essentially be cheating. You would know what it is that you're supposed to predict. And doing this will give your model an artificially high level of accuracy. Because it knows what it's predicting, it shows that it's doing really well. But then, who knows how it's going to act when it actually finds sentences it's never seen before out in the real world. So testing should always be separate from the training set. So now we've split our set, let's say the simpler one, training and testing. And then we need a metric to determine how well our test sentences are predicted by our n-gram model, whose probabilities were derived from the training set. So again, we have the testing set. How well can we predict the test set using the probabilities we derived from the training set? One way to do it would be to calculate something called perplexity, like how surprised your system is by the sentences it sees in the testing set, which is our little simulation of the real world. Let's say we have the test set, and we have in our test set sentences like, I always order pizza with cheese and mushrooms. I always order pizza with cheese and pepperoni. And these have a relatively high probability. This means that your n-gram model, is predicting these sentences fairly well. That it found similar sentences in the training, and so it is very likely from this model that you can derive these other sentences. So this means that these two sets are relatively similar, and that your model is doing a good job at predicting them. But what would happen if there was a mismatch between them? If your testing set had sentences like, I always order pizza with cheese and phone, with cheese and chair, with cheese and chair, with cheese and person, for example. Or what if it had sentences like, I always order pizza with cheese and n-grams? These sentences would be very surprising to our n-gram model because it never saw anything like them. It would cause it a lot of perplexity. You'd find that your model is very perplexed at finding these strange sentences in the test. But because we assume that this test set is going to resemble what we'll find in the real world, we want a model that is not very perplexed. If you have high perplexity, it means that something's going wrong and that somehow your training does not correspond to what you're going to find out in the world or in this testing set. Again, the word for this is perplexity. Perplexity is the inverse of probability. So if something is very probable, your system is not very surprised when it sees it. It's not very perplexed. On the other hand, if something is very improbable, your system is very surprised or perplexed. The best model is going to be the one with the lowest perplexity for the testing set, the one that finds fewer surprising combinations. And the mathematical equation for this is the one we have on the right. The first step is for you to notice that it's an inverse of probability. So it's 1 divided by the probability of our structures. For example, if we have bigrams, it's 1 divided by the probability of each of the bigrams. We're going to use the chains to look at the probability of all of the bigrams in our testing set. And so we're going to multiply the inverse of the first two words of the first bigram by the inverse of the following bigram, by the inverse of the following bigram, and so forth. And so we're going to multiply all of these n times, as many times as we have bigrams or trigrams in the set. Finally, we're going to get the nth root of that number to normalize for how many words we have. This is so that we can compare models with different sizes. Maybe a model was trained on 1 million words. Maybe another model was trained on 1 billion words. So we want to compensate for those differences by getting the nth root to normalize the number. And again, we're pursuing the smallest possible number of perplexity. The number that tells you that the n-gram was least perplexed when it saw the test set. Let's do a toy example with a simple unigram model with 10 words. 0, 1, 2, 7, 8, 9. These are 10 words, and that's it. So because we have 10 words, and each of them occurs only once, each of the words has a 10% probability of occurring. 10% for each of them. So let's plug this into our formula. If the probability of each of them is 10%, the probability for the whole model is 10%, multiplied by 10%, multiplied 10 times. It is 1/10 to the power of 10 times that we found the words. N, big N equals 10. We get that multiplication, and then we have that to the power of, first of all, -1. So that's going to indicate the inverse. And we want the nth root. So we have that divided by n numbers of words. The two big n's cancel each other out. So we have 1/10 to the -1th power. And this is 10. So the perplexity of this model is 10. It means that every time it finds a word, it's very surprised because it was expecting to find equally a 3, a 4, a 9, and when it finds a 0, it's like, whoa, I'm surprised I found that. The whole perplexity when it looks at all of them is 10. This doesn't really have units. It's just a measurement of the inverse of probability. But what we want to have is the smallest possible number for this equation. We want to minimize the equation. Let's look at another example. In one of our previous videos, we looked at the Wall Street Journal and at sentences generated using n-grams from the Wall Street Journal. There was a 40 million token data set, which the author split into 30 million tokens for the training set and approximately 1.5 million for the testing set. From the training set, 38 million tokens, we had approximately 20,000 unique tokens for the training. So this would be approximately 20,000 unigrams, 399 million bigrams, and 7.8 trillion trigrams. So it's the multiplication of all of those probabilities normalized by this is the multiplication of the inverse of all of those probabilities normalized by the nth root. So how many unigrams or bigrams or trigrams you had in each of them. The numbers that you get is that the perplexity for the unigrams is 962. For the bigrams, it's 170. For the trigrams, it's 109. This means that when your unigram n-grams, when your unigram probabilities look at a real sentence from the Wall Street Journal in the test set, it's going to be very surprised because it was expecting just a jumble of the most likely sentences. But regular English sentences don't work like that. They have a flow of more frequent and less frequent words. So this is just going to be a lot of perplexity. The bigram and trigram models perform better because their transitions are better at mimicking the transitions of real English sentences in the test set. We can look at this when we compare the perplexity with the kinds of sentences that each n-gram model generates. Again, the n-gram model just picks things that are the most frequent across the model. And so any English sentence that has a variation of high frequency and low frequency words is going to cause a lot of perplexity because it will only be expecting to find high frequency words or words that it's seen a lot before. Bigram and trigram models resemble English sentences more, and so the perplexity is less. The n-gram models and their transitions resemble English sentences more, and so they're less perplexed when they see real English. So in general, we're looking for the n-gram model that lowers perplexity in the testing set. What we have so far is that we can split the data into training and testing. We use the first set, the training set, to calculate the probabilities of the n-grams, and then we use the testing set to calculate the perplexity of the model. And the lowest perplexity is the preferable one. We could also split it in 3 parts: training, validation, and testing, in case we have something fancier in our model, like a different smoothing algorithm, for example. We can use the training and validation to generate the best possible model we can, and then we can test that by measuring the perplexity of the test set. In our following video, we will continue to look at the evaluation of n-grams by looking at how they handle out of vocabulary words, and how some biases can unfortunately creep into them, and we always have to be looking out for that.